Module 8.2 Theoretical Foundations of UQ. In this module, we learn about error versus uncertainty quantification, sensitivity and reliability analysis, confidence interval, uncertainty propagation methods, surrogate modeling, and UQ at different scales. So we talked about UQ in the previous submodule, and which is basically a science of characterization, quantifying, managing, reducing uncertainties in mathematical, computational, or physical systems. So one of the major challenges in UQ is to reduce high computational expense associated with many repeated model evaluations. This can be achieved through advanced sampling methods, understand how the previous sampling technique, for example, is going to influence my next sampling technique in order to just, instead of doing just brute force sampling, doing something more smarter, and development of computationally inexpensive surrogate models or meta models, or by leveraging high performance computing techniques to kind of reduce the computational time. And there are numerous related tasks fall under the broad classification of UQ, including sensitivity analysis, which aims to quantify the influence of multiple inputs to a system, or reliability analysis, which aims to estimate and sometimes minimize the probability of failure of the system. And there are various tools for analyzing UQ, such as UQPy, Uncertainty Toolbox, OpenTurns, Dakota is a popular one, for example. And we will be touching upon maybe some of them, maybe just UQ Toolbox. And as we were talking about in the previous module, uncertainty could be of aleatoric and epistemic type. And especially for epistemic, there could be coming from model parameters, model descriptions, model foundation, or it could be model parameter itself, or a combination of both. So we'll talk about a little bit about epistemic uncertainty. And as we also mentioned, aleatoric uncertainty dealing with the inherent randomness and some things which cannot be reduced. However, epistemic uncertainty could be due to the lack of data or knowledge or information that we can work on. And there are several proposed mathematical treatments for this, and we will use the probability theory here. And we will specifically study two types of epistemic uncertainty. So model form uncertainty. So for example, uncertainty in selecting the form of a mathematical model, and parameter uncertainty. So uncertainty in identifying the precise value of model parameters. So in general, this epistemic uncertainty can be analyzed. In a way, UQ is converting the aleatoric uncertainty to epistemic uncertainty as much as possible. So notes, their aleatory is basically depending on throw of a dice or on a chance or random. So it's a very stochastic or random uncertainties cannot be reduced. And epistemic uncertainty is coming from a branch of philosophy. There are three main branches of philosophy: ontology, epistemology, and aesthetics. So in ontology, which is basically theory of being and existence, epistemology is theory of knowledge, and aesthetics is very theory of value, aesthetics, and moral. So in episteme is basically knowledge. So you can think epistemic uncertainty is opposite of knowledge or lack of knowledge, right? So in this way, this lack of knowledge could be again due to the model form, or it can be due to the parameter of that particular model form. So that is of our interest in this entire module. We'll be talking about primarily epistemic uncertainty or epistemology, you can say. We are not going to deal about philosophy like ontology and aesthetics. So let's talk about what is uncertainty and how is it different from error. So when we have error, it's basically difference between the measured or estimated value with the ground truth value, and quantifies a deviation of an observation or prediction from actual true value. However, uncertainty is a measure or a range of possible value within which the true value of the variable lies. It reflects the lack of exact knowledge about the value of quantity due to the inherent variability or lack of knowledge. Uncertainty is inherently probabilistic and can be described using probability distribution, confidence interval, ranges, standard deviation. However, error is a specific instance of inaccuracy. It is a single value, and there are different types of uncertainty. We talked about it: aleatoric and epistemic uncertainty. while error could be systematic error or random error. The systematic error could be consistent, repeatable error associated with a faulty equipment or biased measurement techniques. Random error are due to unpredictable variations. Uncertainty is measured through statistical method, probability distribution, and uncertainty intervals, while error is the difference between observed value and the true value. And here is an example given for what is the error versus uncertainty. So about a ruler having a resolution of 1 millimeter, so the length of measurement might be expressed at 100 millimeter plus minus 1. So anytime you do an experimental measurement, you'll have a plus minus value. So that's basically in a way representing uncertainty. This represents the uncertainty due to resolution of the measurement instrument. However, if a true length of a rod is 101 millimeter and the measurement is 100 millimeter, then the error is simply minus 1 millimeter. This could be due to systematic bias or it would be random variations. Now we have already gone through a multi-scale modeling modules. So let's talk about how we can have different UQ at different scales. So at atomistic scale, suppose you are dealing with DFT or density functional theory. So we can have a density functional parameters such as we talked about in that model, choice of exchange correlation functional, pseudo potentials, and we can have a variation of that, a huge variety of that that will lead to uncertainty. If we are dealing with molecular dynamic simulation, we talk about force field, and we can have force field with without bond length angles, without with and without bond angles, with and without charges, and so on. And we talked about different type of force fields. So using one or other could lead to different uncertainty in predictions. Of course, initial conditions are important. So atomic positions and velocities, how you initialize atomic structure, how much velocity you give to them can also lead to uncertainties. Boundary conditions. So what kind of boundary condition you are imposing on them can also lead to uncertainties. Model parameters, model uncertainty. So interatomic potential, for example, there could be different potential model that can lead to different results for the same system. So Yuki helps us to compare and validate these models. Approximation methods. So inherent approximation in methods such as the basis set, key point convergence can also lead to uncertainty. Mesoscale, such as parameter uncertainty, material property, when we are trying to have a prediction on the defect structure, phase field, or grain size, we can have inherent material property that can change, and that will lead to uncertainty. Model parameters, such as in coarse grid modeling or phase field modeling, there are many parameters which can be sensitive to what kind of inputs we are using or how we are getting those input parameters from DFT or experiment that will lead to model uncertainty. Initial and boundary conditions. So initial conditions are also important, similar to the atomistic scale. Model uncertainty, of course, model assumptions. So sometime in phase field or coarse graining, we are having bead spring model or something similar. So we are inducing a lot of uncertainty because of that approximations. And of course, when we go from one scale to another scale, for example, from atomistic to mesoscale, and that boundary between those scale can also lead to uncertainties. Continuum scale, so if you are trying to use, for example, material parameters in your finite element method, such as the Poisson ratio, thermal conductivity, and how much they are varying across different experiments can lead to uncertainties. Geometric parameters such as the dimensions, what shape of components of finite element methods, thickness, and so on can also lead to uncertainty. Of course, boundary condition, initial conditions are also applicable for continuum scales and how do you impose them. And of course, model uncertainty such as the mass density of finite element method, model approximation, simplification of in representing the complex physical phenomenon can also lead to uncertainties. So now we'll talk about probability because this is a key concept in any uncertainty quantification technique. So probability, some of you might have taken courses on that when studying statistics and mathematics. So we'll have a very brief overview of probability theory, not going too much details of that. So probability is a measure of likelihood that an event will occur. So it ranges from 0, impossible event, to 1, or certain event. That is 0% to 100%. The probability of an event is denoted by P parenthesis A. Now, an important concept in probability theory is sample space. The sample space is a set of all possible outcomes. So if you throw if you toss a coin, the sample space is either head and tail. Now, if you have multiple tosses, then the sample space could be not just head and tail, but a combination of head and tail, which is shown on the right hand side. So if you take a coin and toss it, you can have half and half chances of head and tail. But in the second toss, if you have another head and tail, and so on, and now this is a multiplication of 1/2, so 1/8 outcome of head, head, head in the third toss, and so on. And an event is a subset of a sample space. So all this HHH or HHT, for example, are events. It consists of one or more outcomes. For example, getting head in a coin toss in an event. So some of the rules of the probability are they always lie between 0 and 1, because either it can be 0% or 100%. Probability of the entire sample space is 1. So if you know entire sample space, if you and sum it up, it will be 1. For mutually exclusive events such as A and B, which is represented by P of A union B, if you have done set theory before, these are some of the symbol like union, intersections, and so on, is given by probability of A plus probability of B. Random variable. So this is probability, but more often we deal with probability distribution. So, and for that, it's important to understand what is a random variable. A random variable is a variable that takes on different numerical value based on the outcome of a random event. Random variable are typically denoted by uppercase letters such as X, Y, Z. If X represents outcome of rolling a six-sided dice, then X can be represented by either 1, 2, 3, 4, 5, 6. This is the random variable. Now, this random variable could be discrete or continuous. So if you, for example, this example of rolling a dice is a discrete outcome. So, or it takes on a finite countably or countably infinite number of value, for example, number of heads in a 10 coin tosses. Continuous random variable, which is usually quite more often used, is takes on infinite number of value within a given range, such as heights of people. Now let's talk about probability distribution function, or PDF. Probability distribution function describes how probabilities are distributed over the value of the random variable. This can also have two types, because we have two types of variable: discrete probability distribution and continuous probability distributions. So in discrete PDF, we have a list of each possible value of the random variable can take, along with the probability denoted by P of X equals to Xi. So Xi is basically that particular event. It can be represented by binomial distribution or Poisson distribution. Don't get confused with Poisson distribution with Poisson ratio. Same person, but different papers or different methodology. Continuous probability distribution, so it's described by the probability density function, where the probability are determined over intervals, not at particular discrete site, denoted by f of x and x, such as normal distribution, which is extremely popular for uncertainty quantification, and of course exponential distribution. Sometimes it could be combination of exponential plus normal distributions. Now, one of the most popular continuous probability distribution is normal distribution. So we'll talk about that. So the normal distribution is a continuous probability distribution characterized by a bell-shaped curve, as you can see on the right-hand side, and is symmetric around the mean value mu. That's called mu. So the PDF of a normal distribution function is given by f of x. That is the x is our variable, x minus mu, which is mu is the mean and sigma is the standard deviation. And this is a particular form where mu is the mean and sigma is the standard deviation. So there are really some good properties of this bell-shaped curve. For example, the mean, median, mode of normal distribution are equal, which is really good. So it's very symmetric in a way. The curve is symmetric about mean. And some of the other properties are 68% of the data lies within one standard deviation, so mu plus minus sigma. 95% data lies within two standard deviation, mu plus minus 2 sigma. And 99% of the data lies within three standard deviations, mu plus minus 3 sigma. So sometimes when you're doing experiment or theory, you have to know what is the sigma level of your predictions. So there, something like normal distribution and its properties could be useful. Now let's talk about cumulative distribution functions. So Cumulative, as the word suggests, it's a function that gives the probability that x will take value less than or equal to x, denoted by f of x or x. The CDF is kind of cumulative or adding function. So it's a non-decreasing function. For a discrete variable, it's denoted by the particular form sum of p of x equals to t, where t is less than x. So for all the value if you are plotting a curve, all the value from 0 to that value t, you just sum it up. For a continuous variable, it's represented by as integral instead of a sum. That's all. That's all the differences. There are for a normal distribution with mean mu and standard deviation, the cumulative distribution function is given by the error function. So we don't have to derive it, but this is something you should know. What is the cumulative distribution function? And another very important concept in probability is the Bayes theorem. Bayes theorem describes the probability of an event based on prior knowledge of a condition related to the event. This is given by P of A given B is given by P of B given A multiplied by P A over P over B, P of B. So P of A given B is the called posterior probability. It's basically saying that the probability of an event A given the B has already occurred, or P of B given A is called likelihood. So basically on the left hand side, what we have is posterior, or on the right hand side is what we call likelihood. So the likelihood is the probability of B given when A has occurred, and P of A is the prior probability. One on the numerator is the initial probability of an event, and P of B is a marginal likelihood that the total probability of event B. For example, a mechanical engineer is responsible for maintaining a fleet of industrial machineries. Each machine has a component that occasionally fails, and the engineer wants to diagnose the likelihood that a specific type of a component failure, let's call it A, is caused by a observed symptom, let's call it B. Now, prior probability is PA, which is the component failure. If the engineer has historical data showing that this type of component failure occurs in 10% of machines. So let's call it P of A is 0.1, 10%. Likelihood that the P of B given A, if the component has failed, there's 80% of chance that the observed symptom will occur. This is 80%. Marginal likelihood, that is only for the B, which is the symptom causing the failure. The observed symptom can also occur due to their other issues, and that is, let's call it 20%. P of B is 0.2. Now, P of A given B, which is the posterior probability, is now given by Bayes theorem, which is B given A multiplied by P of A over P of B. So you can calculate it to be 40% chances. So this is an example of Bayes theorem. Now let's talk about another important concept called quantile function. A quantile is a statistical measure that divides a probability distribution into intervals with equal probabilities or specific values, which are given percentage of observation in a data set can fall. So kind of, instead of having a broad range, breaking it down. So you can break it down in following ways, either having percentiles, so having them in 100 parts, such as 25th percentile, first quartile, and so on, or quartiles dividing into fourth part, or deciles dividing into 10 parts. The quantile function gives the value below which a given percentage P of observation in a probability distribution fall, and it is an inverse of the cumulative distribution function. Now, the quantile function is used to determine critical values in hypothesis testing and confidence interval. So confidence interval is a very key important concept in uncertainty quantification, and we'll talk about that. For a standard normal distribution, the 95th percentile or quantile is 1.645, which can be derived, meaning that the 95% of the values lie between 1.645. Now, there are different methods of UQ propagation, such as Monte Carlo, Latin hypercube sampling, polynomial chaos expansion, Bayesian inference, Gaussian process regression, and quantile regression. So we'll be basically focusing on 1, 5, and 6. But let's talk briefly about all of them. In Monte Carlo sampling, which is basically repeated random sampling to estimate numerical results. It is named after the Monte Carlo casino due to inherent use of randomness and probability. It was used during nuclear physics in 20th century. It was it was useful in some of the nuclear calculation in making the atom bomb, for example. So it's uh, basically it's a theorem of large number. So large number of simulations or iterations to ensure the results converge to a stable estimate. Some of the steps are: define the problem and objectives, generate random samples, run the simulation for each of the set of the random points, aggregate and analyze the outputs, and interpret the results. Very simple. We'll talk about how to estimate the value of pi and in the hands-on session or the numerical session. Bayesian inference to understand the probability distribution of model parameter based on the observed data. So that is the posterior estimate. Method is Bayes theorem, and basically you define the prior, which you talked about it, collect the data, applies the Bayes theorem, that is update the prior with the likelihood to obtain the posterior and make the prediction and decision. So use the posterior distribution for inference. For example, estimate the probability of a defect item in a manufacturing process. So you have to have the prior, which is the historical defect rate, likelihood, that is observed defects in a sample, and posterior, basically update the defect rate after observing the data. Gaussian process regression. So a Gaussian process is basically a probabilistic method that gives a confidence for the predicted function. So shaded function shown on the right-hand side. A Gaussian process relates the similarity between inputs to their outputs. This similarity, or more formally the covariance, is defined by something called kernel function. In the same way the Gaussian distribution is defined by the mean and variance, a Gaussian process is defined by a mean function and the covariance function. So based on the measurements we have taken, we can infer the value of function at new location called Bayesian inference. That is, P of model given data is given by P of data given model, P of model over P of data. So there are steps in Gaussian process. So first, you define the mean and covariance functions. You compute the covariance matrix kernel. Use the training data to compute the posterior distribution. And now you can make any predictions on the new data for the prior distribution. For example, model the relationship between the load and displacement in a mechanical system. You have to define the kernel functions, for example, radial basis function. We'll talk about that, and compute the posterior distribution for the new inputs. It provides the probabilistic predictions with the uncertainty estimates. So it's not just one value. And it incorporates the prior knowledge through the choice of kernel functions. And there are different types of kernel functions, such as radial basis function, Mattern, rational quadratic kernel, exponential sine square kernel, dot product kernel. And we'll be basically working with the radial basis function kernel. Now, there are, other than Monte Carlo sampling, there are more sophisticated sampling techniques, such as the Latin hypercube sampling. So it is a statistical method for generating a sample of plausible collection of parameter value from a multi-dimensional distribution, and ensures that the sample is representative of the entire range of each input variable. It provides a better convergence and efficient compared to simple random sampling that is Monte Carlo sampling. And it uses something called stratification. So it divides the range of each input variable into probable interval, and it combines the sample to ensure that each interval is sampled exactly once for all the variables. And these are the steps of the Latin hypercube sampling. Similar technique is the polynomial chaos expansion, especially if you have something with multiple variables. This technique can be useful, and it's used for representing uncertainty parameter as a polynomial function of random variable. It transforms a complex stochastic system into a deterministic one using orthogonal polynomials. And the chaos expansion is basically output expressed as a series of polynomial terms weighted by coefficients. And these are the steps of polynomial chaos expansion given below. However, both of the polynomial chaos expansion and Latin hypercube sampling could be very computationally expensive than Monte Carlo sampling. So Monte Carlo sampling is still a very popular technique. Now let's talk about prediction interval. Prediction interval is a range of value that is likely to contain the value of a single future observation given what has been observed in the sample. So the prediction interval accounts for both the uncertainty estimate of the population parameter as well as the variability in the individual observation. So if you know the mean X bar and the standard deviation sigma and the sample size and the t-score, which is basically the corresponding desired confidence, you can calculate the interval. And here's an example of a prediction interval. Suppose we have a regression model that predicts the number of cycles of failure, fatigue life of a component based on applied stress. The model provides not only the point estimate, but also prediction interval for the number of cycles of failure. Let's say the model predicts a component will fail after 10,000 cycles with a 95% prediction interval of between 8,000 and 12,000 cycles. This means that there is a 95% probability that the actual number of cycles to failure will fall between 8,000 and 12,000. This interval outcounts for the variability in the fatigue life due to factors such as material properties, manufacturing, inconsistency, and operating conditions. It means the model predicts 10,000 cycle to failure, and the model also provides a range. Now, if we have lower and lower uncertainties, we have higher confidence, for example. Now, one of the important concepts in uncertainty modeling is surrogate modeling. So surrogate basically means a substitute or replacement. So instead of having a very complex model such as DFT or finite element method, we will try to replace with their corresponding surrogate model. So the methods to generate surrogate modeling is polynomial regression, Gaussian process regression, Kriging model, neural network, radial Basal function networks, and support vector machines. And most of the machine learning surrogate model that we developed in the previous module can also be considered as surrogate models. And in addition to having standard deviation as a measure of uncertainty, we can have various other types of metrics for uncertainties. For example, validity. So validity assesses how well a model prediction reflect reality. Imagine a model predicting the deflection of a bridge under the load. So the high validity would mean that the model's predicted deflection closely matches the actual deflection measured during the real world load test. Sharpness is another good one. The sharpness measures the concentration of predictive distribution. A sharpness distribution indicates the model is more confident in its um, prediction by providing a narrower range of possible outcomes. So basically, if you take a standard deviation of each of the outcome and take an average of that, that's basically in a way represents sharpness. So consider a model predicting the failure life of a machine component. So the high sharpness would imply the model predicts a narrow range of cycles the component might last before failure, signifying confidence in its predictions. NLL, or negative likelihood, log likelihood, is a measure that disagreement between the predicted probability distribution and the actual outcome. So lower NLL indicates better agreement. Similarly, there are other metrics we'll not talk about too much, such as continuous rank probability score, CSRP, and so on. And you can learn about it in the uncertainty toolbox.